So I'd like to welcome Professor Avideh Zakhor from UC Berkeley. She's been a professor there since 1988 and actually started working on the project she's going to show us today since about the year 2000 in automatic 3D reconstruction of city models. And this is something obviously we're very interested in, and this talk's going to be broadcast externally, so if you have any questions of a confidential nature, save those till after the talk. Okay, thank you.
Thank you very much. Can everybody hear me okay? Great. So I thought what we would do is just start with a little demo. What I'm going to talk about today is a method that we've been developing at UC Berkeley over the last 6 years or so for automatically building three-dimensional models of cities. And we've inserted some of those models inside Google Earth, which I know most of you are probably familiar with. So I'm asking Steve, why don't you navigate in and out a little bit so people can see the model within the bigger context. Zoom out. They can see the model within the bigger context of Google Earth. So if you look, you see that the model is sticking out right here, and it's a 3D thing, and the rest of it is just the satellite imagery from Google Earth. And now we can zoom in to go to Berkeley. This is downtown Berkeley. This is Shattuck Street. That's the BART station, entrance to the BART station. This is the Powerball building. And just to make sure that you get a sense of the 3D, why don't we turn the downtown Berkeley model off? And this is what you would have gotten with Google Earth. And now turn it on again. And so you can see that there's a real sense of three-dimensionality that gets added on and off. Why don't you navigate a little bit more around campus and maybe now turn on the campus data. So this model for downtown Berkeley, as you'll see in a minute, was generated by using both ground-based data and airborne. Now, we've also generated the campus data, which only uses airborne data, and that's down here. Okay, so we'll talk about that a little bit, and why don't you turn that on and off, just real quickly. Okay. So I think I'll stop now with the Google Earth and get on with the main part of the talk when we exit out of that. And I'm happy to, at the end of my talk, I'll send you pointers. You can download these and add it to your own Google Earth and play with it. Why don't you load up the... Okay. Okay, why don't you fire up my PowerPoint now? Okay. Great. So what I'm going to talk about for the next maybe half hour or 30 minutes or so is a quick overview of how we generated some of these models. This is all done at my lab at Berkeley, which is called the VIP lab, Video and Image Processing. Is this? How do we go down then? Oh, which button did I push? I guess it's the mouse. Okay. So just before going into the details of that, I wanted to quickly give an overview of other projects that has been going on in my lab over the last few years. Being at Google, I can't not talk about video similarity search. This is a thesis that was done by Samson Chong in 2004, where we recognized in a very, very large database of videos, the nearly identical videos. There's quite a bit of work on multimedia networking and streaming, especially over wireless. Some work on compression of VLSI data, and finally 3D modeling of urban environments, which is something I'm going to talk about right now. So a bit of acknowledgments. This work was sponsored by ARO, Army Research Office, under a University Research Investigation Program, MURI, from 2000 to 2006. Google generally started support in 2006, and we're very grateful for that. We've also received what's called a DURP Equipment Grant from Air Force in 2006. And a whole host of postdocs, graduate students, undergrads, and research staff have been working on this. And 3 of my students are here, and you're welcome to talk to them after the talk if you're interested. So the goal is to generate three-dimensional city models that are useful for both virtual walkthroughs, drive-throughs, and fly-throughs. And we want it to be as photorealistic as possible. And there's a whole host of applications. And I'm sure for this crowd, I don't really have to motivate the problem too much. And our objective has been to do it in an automated way, fast, scalable, and photorealistic. Just as a way of background, there's been a lot of other work on city modeling. For example, Seth Teller at MIT developed this system where you would park your apparatus at a particular location in front of a building in a city, scan for 30 minutes or 20 minutes, then move to the next building, scan it, etc. What differentiates this work from existing work in the literature is that we actually acquire our data in a very fast, non-stop and go fashion. And so that enables us to generate models fairly quickly. And you'll see that in a little bit more detail. So the approach that we've taken for full-blown modeling is really come up with two models. A model that's been generated by a acquisition vehicle that drives on the ground like a truck. And that results in what we call ground-based modeling. And that really models the facades of the buildings. And then we do what's called airborne modeling, where we have helicopters as well as airplanes collecting laser data as well as imagery from the top in order to build a 3D model of the rooftops. And we merge those two things to come up with a 3D city model. So a big chunk of our effort has to do with registering the different sources of data and fusing it together so they all line up. You get something nice and good. So I'm going to talk very briefly about the ground-based modeling. This is our acquisition vehicle parked in front of Corey Hall at UC Berkeley. It consists of this board here that has three things. It has two Zik laser scanners. One of them is vertical. The other one is horizontal. And it has a camera, a Sony camera. And the data from all of these things is connected through these wires to a PC that's sitting in the back of the truck, getting powered by the battery on the truck itself. And as I said, we call this drive-by scanning. We collect the data as we're driving under normal traffic conditions in the roads. We don't stop and go. So here's the basic system. You have the vertical laser scanner that takes a swipe like this vertically as the truck is driving. And the idea is to stack up these vertical laser scans next to each other in order to build the 3D profile of the facade of the building. Okay? But in order to know how far apart you stack these vertical scans, you need to know how much the truck moved. You essentially have to localize your truck. And that's not a terribly easy problem. And the way to solve this localization problem is to use a horizontal laser scanner and successively match horizontal laser scans in order to deduce the movement of the truck so that we can then stack these vertical scans at appropriate distance from each other. And synchronized with all of these things is a camera that acquires texture together with the laser scans as we move along. So this shows the process of pose estimation, in other words, localization of the truck using horizontal laser scans. So this is a visualization of horizontal laser scan at, let's say, time t0. This is the next time step, t1. And what you want to do is you want to come up with the translation and rotation parameters that makes these two scans match with each other. And to do that, you solve an optimization problem, which I won't go into the details of it. But once you do that, then you can recover these little vectors, delta U, delta V, and delta phi, concatenate these in order to reconstruct the path. And this shows the reconstructed path by successive matching of the horizontal laser scan. And if you then use this reconstructed path to superimpose the horizontal scans, you get this blue line. And ideally, you like to have this blue line to be as thin as possible so that the successive horizontal laser scans match each other. So if they weren't matching, this blue line would be very, very thick. So this method is okay, but it's not great. If you start at location 1 and drive all the way to location 2, And this is the reconstructed path that you get, the red. And what's underneath this is the digital surface map that we've obtained aerially, in other words, a height field of the area underneath. And you can see these are the streets in a Manhattan structure. And as you can see, the red path goes all over the buildings. It doesn't really follow the streets very well. So something has gone wrong. We need to do, what's gone wrong is that, especially at turns and other situations, the method doesn't quite work, and errors also accumulate. And to prevent errors from accumulating, you have to do what we call global correction. And that's exactly what we did next. And the way you do that is you say, okay, I'm going to start with either an aerial picture or an aerial DSM, digital surface map. This is just a height field using laser scans. We're going to use this later on for our rooftops anyway, so we might as well just utilize it for localizing the location of the truck. So if you use these two things, detect the edges, and then match these edges with the horizontal laser scan, then you can have a shot at globally correcting it and making it work. So that's exactly what we did, is we applied what's called Monte Carlo localization techniques using particle filtering. This is explained in this paper that's listed here. And we matched the horizontal laser scans essentially with airborne edge maps, okay, in order to localize the vehicle. I won't go into the details of Monte Carlo localization, but it essentially consists of a motion phase where we increase uncertainty and a perception phase where we decrease uncertainty. And this video here shows you the result of particle filtering. So what we see here is the DSM, the airborne depth map. And the blah here is the probability density of the location of the vehicle based on this technique. The red in the middle means that the thing has the highest probability of being there, and the yellow means the probability decreases. But the good thing is that the blah kind of moves on nicely and smoothly way in the middle of the street, even though we change lanes. And I believe if this video is the one I have in mind, even when we make a right turn, the blah stays within the streets. These are the edges of those. We now switch back to the DSM again. So these are, there's points at which this thing disintegrates a little bit, but composes itself back again in the middle. And we used, for those of you who are familiar with this particle filtering, we used 10,000 particles in order to accomplish that.
And there's no GPS?
There's absolutely no GPS. That's a very good point. We dwelled about this problem quite a bit, and we decided not to go against it because GPS doesn't work in places where there's high buildings or indoors. That's correct. If you had GPS, you didn't have to do any of these tricks. Yeah?
So if you have like a gross mismatch between consecutive frames when you try to align the 3D data, do you have some way of recovering? For instance, you can have an occlusion in the camera by another.
I think that's where the global edge thing from the top will help you to correct those situations.
But even if it's moved, because just one frame will change the orientation of your whole projector.
Yeah, but you're banking on the fact that your laser scanner runs at 75 hertz. And compared to the speed of your truck, that's pretty fast. So you're right, there will be occlusions, there will be some changes. The matching is not perfect. But in almost all the experiments we've done with tens of minutes or hours of driving, together the combination of airborne and the horizontal match has resulted in very good localization. Yeah?
Would it help if you scan more than just one direction, like if you look to the left as well as to the right?
Yeah. Oh, wow. Yeah, there are some interesting architectures that we're considering now to have two laser scanners at 45 degrees because that would also deal with the occlusion problem. That's correct. So in that Monte Carlo localization situation, not only do we can calculate the orientation, but also Z, which is the height of the truck if you're going up the hills, for example, in Berkeley, or the slope of where you're going. So it gives you all the parameters kind of in one shot. And whereas what we got before was localization that looked like this, now what we get is with this kind of localization, which is perfectly aligned with the streets. And just to give you an idea, this was a 78-minute drive resulting from 2 data acquisitions, 24.3 kilometers, 600,000 scans, 85 million scan points, 19,000 camera images for this drive within Berkeley. And now that you've localized your truck, you can then stack these vertical scans at the appropriate distances from each other and get a point cloud that's shown here. For those of you who are familiar with Berkeley, this is the entrance to the BART station and as you go down. And so the next thing that you do is, question, yeah?
Does this basically allow you to kind of get rid of cars or people and other things?
I'll talk about that in just 1 second. So the next thing you want to do is triangulate or tessellate this. And generally, if you have a point cloud, triangulated it in the most general way is a very difficult problem. But we have the fortune of the fact that these vertical scans are given to us in order. So that makes this triangulation problem extremely easy. And after you triangulate a point cloud that like this, you get something like that. And at the first look, it looks pretty disappointing. These holes are there because the infrared laser goes right through the glasses of the windows. There's cars here, there's trees that block the window. But after some processing, you can do foreground removal, which I'll talk about in just a second, as was brought up. We fill out some of these holes, and we get something like that. And I'll talk about the step from here to here in just a second. And then we texture map it, and we get something that looks like this. So if you just, this is kind of reinforcing what I just said a second ago. If you just triangulate from you get something like this, which looks semi-okay from the front view, but from the side view, there's all these garbage kind of flying. So how do we clean it up? So we apply standard image processing techniques, okay? We transform each path segment into what's called a depth image. So this is a tree in front of a building, cars in front of the trees, etc. And what we do then, using the histogram analysis over the vertical scans, we try to do what's called foreground-background separations. The idea is that the trees and cars are at a distance from the buildings, and therefore by looking at this histogram, we can remove those. And this works fairly well in downtown areas where there's a fair distance between the trees and buildings. For residential regions, as I'll talk about in a few minutes, it doesn't necessarily apply. So you start with this kind of a image. It's separated into foreground and background, as I was just talking about. So the background ends up being the buildings, and the foreground is the trees and the cars and various other things. And you apply a bunch of techniques that I won't go over into details, but to fill out the holes in the background, which is the buildings, you apply some interpolation techniques, and at the end you end up with a clean background which consists of your facades of your buildings. This video here shows the hole filling process, and as I said, in real life we actually do the foreground removal before the hole filling, and once you exit out of this. And the next one shows foreground removal.
Fill the hole for the membrane?
It's pretty much in painting. And actually, filling holes in the 3D data is a lot easier than texture filling. I'll talk quite a bit about texture filling. Okay? And while we're at it, why don't you show the texture mapping one as well? I'll explain how the texture mapping works in a little bit more details in a second, but this is essentially University Avenue, McDonald's, Taiwan restaurant, the futon thing, etc. Okay.
Can you go into a little bit more detail about how you interpolate over the 3D holes?
I didn't make any slides on those.
Yeah, but just a few words.
Basically, you look at the hole from the left, from the right, from top and bottom, and you do interpolation. But you try to do interpolation while you're preserving the edges, kind of a thing.
So you're not just fitting a plane to the hole or something more meant to.
I think we do a little bit of that. After we decide what's going on around it, you try to fill kind of something that fits the neighbors, but also as smooth as possible in the middle. If it can be a plane, it can then that would.
So you try to propagate linear features outside the whole.
Right. We're not. I could tell you this is not something that was terribly difficult. So the texture hole filling was a lot more problematic. I mean, that required a whole master's thesis, let's put it. Whereas the 3D hole filling was, I would say, a month worth of work. It wasn't.
If you have a hole in the 3D surface, and the laser is giving you the relief of the bricks, you wouldn't want like a smooth interpolation. You'd want more bricks.
That's right. That's right. And the answer to that is that we're making up data anyway, and both for texture and for 3D. And at the end, what the best method is subject to a lot of debate. You're right. Because
depends a lot on what your goal is. If your goal is to make a picture like this, you do one thing. If your goal is to fetch a model into SketchUp, or you might do something different.
And actually, if your goal is to satisfy the military guys, they don't want you to handle the data in any way, because, I mean, my goal was to generate something aesthetically beautiful. And let's say Hollywood wants that, the game companies want that, architecture firms want it, but the military wants accuracy. They don't want you to mess around with the data and make it up kind of as you go.
Can you make an underlying assumption that the distribution of beds is bimodal? Or
The distribution of the
beds is bimodal?
You could make that assumption. Most of our holes actually a lot of them were the windows, because it went right through the glass. And so extending the surrounding area was kind of good enough. So this shows without processing and with. And there's a few other examples that I haven't included here. And next, we move on to what I just talked about, texture mapping these images. I showed the video already ahead of time. But here's the basic idea. We've removed foreground objects like trees from in front of the buildings. So in the 3D model, there's no 3D model for the tree anymore. That caused the hole in the building, and we filled up the hole. But now we want to do texture mapping. And if you really want to do texture mapping, you should make sure the texture corresponding to the tree doesn't get mapped onto the building, because there is no more tree. And so the question is, how do we identify the pixels corresponding to the foreground objects that we just removed from our 3D data in our images? And it's not, your first thought might be, oh, the laser scan and the camera are synchronized, and they are. Therefore, we can back project into the images and figure out the locations in the images where we removed the foreground objects. And you're quite right, we can do all of that. But the resolution of the laser scan is quite different from the resolution of the image. So while this method works a little bit, it needs to be refined. So, for example, if you apply this method, you can remove most of the tree, but a little bit of the tree residual still remains in your images, and you want to get rid of that. So the technique that we use, and this was the master's thesis of Siddharth Jain, who is a PhD student at Berkeley, was to use optical flow and region growing techniques in order to more finely define the foreground objects like the trees, like the cars. And that worked pretty well. So you can see that these dotted regions are the foreground objects as detected, and we've removed it from in front of this power bar building. This is Ross, and we've detected these white tree points here, and we've removed the tree entirely from in front of this building. So what are the steps for texture mapping? So you start with these, after you remove the pixels corresponding to foreground objects, you have a series of images like that. They overlap quite a bit with each other. You make a mosaic out of them. And now, because you've removed foreground objects, once again, you have to invent data for them, because now we're trying to figure out what's in the background and fill it out. And again, for downtown regions, this foreground-background separation works very well because the objects are well separated. For residential areas and others might not be very appropriate to do so. But anyway, so we next applied texture synthesizing techniques, which is essentially in-painting kind of techniques, and I'll explain that. So to go from here to here.
Window, the bottom panel, that's not an in-painting, it's a missing region. What the window?
I'll explain that in just 1 second. 1 second. It's the example that's on the next slide. So what we do is a copy and paste method. For some regions that are easy, you can do in-painting and interpolation, simple things. For other regions like this, you can do copy and paste method. So you're missing here, you get a window, you go around this, and you compare that with other parts of the image, and see these bricks are kind of a clue as to finding out what ideally you should put here. So you do a search around this region, do copy and paste, and you gradually start building in those missing parts. No, it's not supervised. There's copy and paste and there's interpolation, and depending upon how big the hole is, we choose between one or the other.
That choice is automatic?
That's automatic, yeah.
What kind of overlap do you have between successive bias? How much do you use successive images to
This would be kind of a good example. Yeah. We actually, a whole lot of our images could not be used because the camera was pointing right at the sun. Those images got thrown away right off the bat. And then I would say that there's probably 30% overlap between successive images. The camera, the intensity camera, we were running it at 5 hertz. And probably the speed of the truck was about 25 miles an hour. That's the speed limit at Berkeley. And I doubt if my students exceeded the speed limit, but unlike their advisor, they actually stick to it. And by the way, that 25 miles an hour results in these vertical scans to be approximately 5 centimeters apart if you're, I don't know, 10 meters away from the building or something. So your resolution of these facades is very high, and you could even argue it's too high, because it's actually the reason we had to bring a PC to show some of our models and not a laptop, because the model is so rich, and that's the reason that we slow down Google Earth so much when we put our 3D models in it, because it's a lot of data, and we have to do a lot of simplification, as I'll talk about in just a second. So this shows the copy and paste process. We do it to speed things up, we use a pyramid in order to do the search for these regions. First, do the search over smaller regions, then a little bit bigger, and then the final image. And this is before and after. So for these regions, for this picture, the holes were large enough that we had to apply copy and paste method. And this is another example. By the way, yeah. I already showed the texture mapping video. In the interest of not crashing PowerPoint again, we'll just skip this. Okay, so now comes to the question.
Yeah. Do you have cases where copy and paste just hallucinates
Generate something terribly bad?
Hallucinate something completely inappropriate.
Not that I know explicitly right now, but we've tried this on this whole thing on a 4x4 block of downtown Berkeley, so it's possible that would generate. It could happen. The copy and paste method is quite compute intensive, actually. And if you skip that part and just interpolate, then things would go a lot faster. But of course, you wouldn't be able to, for example, recover that arch in that building. Okay, so the rendering of these things. Actually, the very first time we generated these models, we were like 4 days away from our government review in Washington, and I kept telling my students, okay, where is it? Put it on the laptop, I want to see it. And they said, you just don't understand, it doesn't fit. There's no URML browser that can enable us to see this model. It's kind of like inventing something that you can't even observe it. It's like a phantom of your imagination or something. Anyway, so the ground-based models, per path segment, they have roughly 270,000 triangles, or 20 megabytes of texture. So many million triangles for 4 downtown blocks, about 4 million. And 400 megabytes of texture. So these are all difficult. So you have to build what's called levels of details and generate scene graphs to do that. And sure enough, we applied techniques like QSlim to go from something that was more high resolution like this, something that was low resolution. Here, the geometry is 10% of this one, and texture is 25% of the original. And one of the areas that I would like to work on in the future is push QSlim further and further in order to generate even simpler, decrease this number to maybe even 1% while preserving the approximate shape of the buildings. This is something actually Ming, who's sitting here, worked on a little bit as part of his class project at Berkeley last semester. So you can build these scene graphs with different levels of detail by making these cuts along a segment that's shown here.
Generate using audience texture for the parts of the building that are occluded, like the top of that balcony.
This part, you mean?
No, the upside of that balcony, for example.
Here, you mean?
No, both. So the part that's occluded is actually texture. I mean, if I go and look at it from above, what will I see?
Oh, you mean behind this thing? Nothing. I didn't put that. And actually, another good point that I didn't mention is that this top part is blank because our camera wasn't pointing high enough. And I can get into all the details of why the camera wasn't pointing high enough and all of that. But basically, the next revision that we will do to this system, we're going to have multiple cameras. If the camera was pointing too high, the sun would have blocked it 90% of the time. You would have useless pictures. So you have to come up with a scheme where you get useful pictures at the same time as covering the top of the buildings. Correct. You'll see that in just a second. And unfortunately, the aerial has lower resolutions, and so you marry it to the high resolution ground base, and there's the visible lines that shows the difference.
Well, I would think color correction would address that. It's not even clear here with the aerial photography.
I'll show it in just 1 second. The resolution mismatch is horrendous. That's to put it mildly, I think. Okay, so then after all is said and done, you have this interactive rendering with a web-based VRML browser, which Steve will show in just a second. So this is the 12 block facade models of downtown Berkeley. This is one facade. This is the street behind it, et cetera, et cetera. And when we put it all together, it looks something like this, which looks a little bit like a ghost town. But if you put the rooftops, it'll look better. So just move on to that. Just to give you an idea, the acquisition time for this was 25 minutes, and the processing time was 4 hours and 45 minutes on some Pentium machine. And it's fully automated. We didn't hand tune any part of it. By the way, this number does not include the copy and paste part. Here we reduced that requirement. We just did interpolation all across. So that's an important point to emphasize. So Airborne modeling, hired a company from Southern California to fly their airplanes over Berkeley to collect laser data. They have the laser equipment right on the plane, and they set everything up. And then we hired a helicopter pilot together with one of the students to take pictures at a separate time, at a different location, etc. And these pictures are oblique airborne images that would hopefully paint the top of the buildings, the upper part of the facades where the image, the camera did not, the ground-based camera did not capture.
Did you pose estimation for that?
For this one?
Yeah.
Yes. And Ming, who is sitting here, is refining the scheme that I'm going to talk about in just 1 minute. That is a hard problem. So this is the flow diagram of our airborne processing. You start with the airborne scans. You do DSM generation, DSM post-processing, triangulation, and then image registration, selection, texture mapping. I'll go over each of these in just a second. So the airborne laser scans look something like this. We have to regrid it on a square grid in order to get it into a format that you can work with. And figuring out what the optimum grid parameter is not that difficult. And after you regrid it, some grid points have multiple data, and some of them have none. So you have to do some interpolation again to get a height field. And after you do it, you get something like this, which is called the DSM, or Digital Surface Model. And if you just connect everything up and triangulate it, it looks something very noisy. And do Q-slim simplification, it looks something very noisy. And the reason is because the rooftops would, well, specifically if you zoom in, you see that the rooftops look very bumpy, the edges are very jittery, and all that. So you go through this set of processing steps, which I unfortunately don't have too much time to go over it, but the highlight of it is this ransack polygonization technique that will divide up the rooftops into, segmented into planar regions. Planes can be either horizontal or at an angle like this, but we're not fitting quadratic surfaces or anything like that. And at the end, you end up with this kind of a model, and now your DSM after triangulation looks neat and clean like this. Next, texture mapping from aerial. So this is the helicopter, and we did a 20-minute ride, 5 megapixel digital camera, 17 images, and it's from both rooftops and facades. So now the question that this gentleman asked comes up. How do we determine the pose of those images, or the airborne images? So the approach we took, so before I even get to the approach we took, you can just use Lowe's algorithm, have a human being click on 7 points in the image, 7 points on the model, those are the correspondences, hit the go button, and in like, what, 30 seconds or 1 minute or something like that, you get the match. So that is very easy, but the problem is it doesn't scale. If you have thousands of images, it doesn't scale. So for the models that I've shown you, what we've done is we've actually done the human processing part. However, after we compute the answer using a human correspondence type approach, we perturb that by 5 degrees, 10 in this direction, 10 degrees there, and so many meters in the z direction, and ask ourselves, if we know approximately the pose, if we had INS on the helicopter or something like that, could we have arrived at those same poses that the human operator could get? In other words, we perturb the true answer, we try to arrive at it again. And this is the technique we used, and you'll see in just a second, this method, assuming certain amounts of uncertainty in your GPS and INS, etc., results in a processing step that's 24 hours per image, which is very large. And that's exactly why Ming, a fellow sitting here, is working on the next generation scheme, which I'll talk about very, very briefly in order to speed this process up. So what's the step that takes 24 hours? Well, you compute 2D lines in your images, try to match them with 3D lines in your model. And you form what's called this cost function here, and essentially you do an exhaustive search over your 6-dimensional pose space at very fine increments in order to find a particular pose that matches, that results in the best possible match between these 2D lines and 3D lines. And so here's an example where the match is excellent. We have a good match. And here's an example where it's not, where the green line doesn't line up with the edges of the building. So this technique is okay, but this 7-dimensional search space is extremely non-smooth. If your step sizes in your exhaustive search is a little bit too high, you could easily miss the peak in this optimization problem. So essentially, steepest descent is inapplicable, and that's why you have to do exhaustive search to do that. And this slide shows you what I said earlier, which is if you have absolutely no idea of where your helicopter is in this column here, 360 degrees yaw, roll, 180 degrees pitch, 1,000 meter uncertainty in your GPS, this is the number of poses you have to go through, and it will take you 3.4 million years. If you have low-cost GPS, it takes you 25 hours. which is the number I threw around a minute ago. Now, if you had differential GPS with a little bit more expensive INS, et cetera, you could get it done in 40 seconds. And what Ming is working on, I'll talk about it in just a second, is a method of using vanishing points and other techniques in order to achieve something like this, 40 seconds or a minute or two, but using low-cost equipment. And I'll talk a little bit about that. Sure.
When you discussed manual registration, you mentioned David Lowe's work, but of course, in matching images to models, he did exactly edge extraction, had a 3D model, matched it. He was doing this at 30 frames a second or something. What's the... Because
he was doing it an image to image, not image to 3D.
No, it was a 3D model, but he was matching to image.
You mean he had a 3D model, he had images of it, and he was matching that?
He had an image of a person using a hand drill. He does edge extraction and matches that to edges of a wireframe model. He just as opposed to the real model to match the edges of plastic.
I'd have to look at the details of that. But yeah, actually I'd be very interested in So now I get into fusing texture from multiple images. So each of our triangles in our airborne model has been imaged by more than one picture. And so the question is, which texture do we use in this series of images to paint that? And we use a series of heuristics that's listed here. You want to pick an image that has the highest resolution for painting that triangle. You want to use visibility considerations, normal vector considerations. The triangle would look a lot better if the picture was taken head-on than, for example, from the side. And also neighborhood consistency. Ideally, you like triangles that are next to each other to receive their texture from the same images so that you don't have so much jitter across the triangles. And so this picture here shows in your downtown 3D airborne model, this shows that these are the regions that were painted by this red image. These are the regions using those criteria: blue, and gray image. And finally, the last thing you want to do is, because there's a lot of overlap between these images, and because you only use a small piece of each image, you build what we call an atlas image, which physically doesn't have any meaning, but it has texture composited from all the different images that's actually being used. So this is what your graphic cards at the end will use in order to do the rendering of your airborne model. Instead of having to store 225 megabyte texture, you want to have just 72 megabytes. So here's an airborne only model with all the different things going on. Airborne only model from a different view. And finally, model fusion, and I'll go over this very fast just so that we can look at some more videos. So what you do is, if you look at the airborne-only models, down at the bottom, these models don't look very good because the resolution of the images is low, and because it's a rectilinear model. We had the rooftop segmentation, and we just brought it down. So the details of the 3D model at the street level is not very good. So you divide your model into segments, remove the part of the airborne model that's touching the street, which is shown in this gray area here. Insert the ground-based model, which is shown here, and this part of the ground-based model doesn't have texture, but it is still ground-based. You can see that. And as you can see, there's some holes between the ground-based and the rooftop model. And what you do is we apply what's called a blend mesh to connect the two things together. And finally, you're slapping the airborne picture in order to paste or paint the upper part of the building, which didn't have. And so you can see that there's quite a bit of resolution difference and color adjustment that needs to be done. Yeah?
If computational enough object, then it's very tempting to apply your copy and paste.
Exactly. That's very true, especially because buildings are highly repetitive. That's a very good point. So this is it, and this shows other examples of both positive and negative. The airborne image is very nicely aligned for the ground-based image, showing that the truck localization worked very well, and the registration problem has been solved nicely. But the downside is that there's resolution mismatch. And those can be solved by either collecting the better data at the ground level, or just as this gentleman said, just extrapolate this data to make up this data. Same things here, same thing here, same thing here. That's downtown Berkeley. Another fly-through model. So I think at this point I'm going to have Steve, before I get into future work, just show us a demo of a VRML demo of this downtown model. Just hit the this thing. So this is the entire fused model for the 4x4 block of Berkeley. Did you hit the drive button?
Yeah, no.
Why didn't you do that?
You have to click it.
Okay, why don't you do that? So this is the walkthrough of, and this was the model that we inserted inside Google Earth at the very beginning. This model has, why don't you hit the button? Okay. So this model has 3 levels of detail, whereas what we inserted inside Google Earth just had the medium level. And one of the reasons was that if we tried to put the high resolution version of the model inside Google Earth, it was too much texture. It would just not be smooth on any of the machines we had for interactive rendering of it. Okay. Thank you. So, few words on future work. It's actually 50 more slides on future work, but I won't talk so long. It's very hard to compete with lunch, so try to wrap up everything in 8 minutes. So, scaling to very large regions is a big goal of ours, and I'll talk about some of our thoughts on that. Dealing with trees and vegetations, this foreground background stuff, extending to indoor modeling, integrating the 3D models with sensor networks. That's an area that the government is funding us in. Streaming these 3D texture models to maybe handheld devices, and also model update. If you've already collected a bunch of data and now some of the buildings are gone, some new ones have appeared, how do you fuse these two models without having to start everything from scratch? So scaling to large regions, so far we've used laser data and camera imagery, both from airborne and ground. And I can't stop wondering whether we could have simplified our life if we just didn't have ground-based laser scan, for example. Or how would our models look like if we just have airborne laser and camera? And that would scale very nicely, because when you go up in the air, take one picture and it covers a huge area. Or if you can take even a video camera up in the helicopter and it covers a huge area. So if your goal is just to have fly-throughs and you don't really want to land in the ground and see what's going on at the street levels, then the airborne-only models can look very nicely. However, for airborne-only models, as was pointed out during this talk, the pose estimation for helicopter images is still a big problem. And that's one of the things that was a 24-hour thing that I was talking about. Your choices are 3.4 million years, 24 hours, or 40 seconds, depending upon what kind of equipment you have on the helicopter. So what Ming is working on is methods of developing low complexity pose estimation techniques for airborne images. And so the lines of thinkings that we have is to use a electronic compass and hooked up to a camera, take pictures, apply vanishing point kind of techniques to recover some of the cameras, then do 3D feature matching both from the 3D model to the images. And this is all work in progress, so there's no results, but merely outlines the kinds of things that we think we're going to be doing in the next 5 to 6 months, and apply a ransack type algorithm to do this correspondence and in order to derive the model, the parameters of the camera. And we're hoping that this approach of using vanishing points will be less time consuming than the exhaustive search that took 24 hours per image. The other problem is trees. What do you do with trees in residential areas? What do you do with trees in downtown type areas? If you don't remove the trees, sometimes your model could become very cluttered. On the other hand, if you remove it, you have to make up for the texture behind the trees, and that's not always easy. John Zakhor was a student who worked on it, got his master's thesis in 2006, and he came up with a tree detection algorithm using registered aerial LIDAR and imagery based on segmentation and classification. We used region growing for segmentation together with training, and classification we used support vector machines. These are the features that we used for segmentation: height variation, normal vectors, hue, saturation value, etc. And this is the weights of the different features. So as it turns out, the height variation is just about the most, you apply normalized cut technique, and you find out that height variation is just about the most important feature in doing that segmentation process. Then you do support vector machine classification, and you start with the LIDAR and airborne data, texture mapped. That was for residential region, and that's for campus. This is the result of your segmentation, and this is the final result of tree detection. So the green shows trees that our algorithm actually detected as trees. The blue, dark blue ones right here are, they were not trees and they were incorrectly classified as trees. And the purple, they were incorrectly classified as non-tree, but they were really trees. So you can see the algorithm mostly works. This work is going to get published in IEEE Geoscience letters in about a few months. And this is the same thing for campus data. The green is the trees, and we pretty much detected most of them. So ideally, you like to have very little purple and blue and detect all the greens properly. Pardon?
I'm puzzled by the incorrect non-trees on the top of the
How could it detect it as non-tree? Is that what you're saying? Why is it that it does it?
Are you saying that those things are trees?
The green is the trees that we detected as trees.
Right, and the purple are trees that weren't correctly identified as trees? It's an incorrect non-tree, which means it's correctly a tree.
That's correct, and you're right. Why is it that maybe these two need to be flipped? Yeah, it depends what the meaning of this thing I put down here is. Yeah.
So you can actually detect chlorophyll directly by ratio of your infrared smart. So if you put infrared, camera up there, you can directly detect vegetation. You wouldn't need to use any kind of.
Excellent.
You have infrared reflectance from your laser scans.
Right.
So you have one infrared picture combined with your optical.
Right. And that could easily do. Very interesting. Thank you. Let me go back to this one. Yeah. Actually, that's a good point. I was never brought up, even though this talk has been given before. So I'll look into that and see why the purple is on top of the building. This is the false positive rate versus true positive rate, and the purple line is this segmentation classification technique, and the green is kind of the same approach if you just skip the segmentation and do it on a point-wise way. And this is for residential data, and this is for campus data. So you can see that actually segmentation does help you to accomplish this task. Portable modeling, possibly indoor. There's nothing to stop you from applying a lot of these things indoors. Because we didn't use GPS outdoors, we're now uniquely qualified, I guess, to apply the same kind of techniques for indoors. I don't think we want to carry a horizontal and a vertical laser scanner. That's too heavy. I think Steve would know the numbers, but it's about 10 pounds each, or isn't it? Yeah, so 20 pounds I think is excessive on anybody's back. But you still need to recover the six-dimensional DOF, but together with some INS and camera imagery, you can recover those things. There's a lot of nice things about indoors. You're walking a lot slower than a truck was. You're not doing 25 miles an hour. As you enter rooms, you can click a button. As you leave it, you can click a button. Therefore, you can close loops. There's a lot of nice tricks you can play. You can have additional sensors like gravity and altitude, etc. And update is easier indoors than it is outdoors. So you can use the same kind of sort of equipment, maybe just one vertical laser scanner, some cameras, and some low-cost INS and IMU units. Just a quick cost calculation would be something between 7 and 14K to build the equipment. The power requirements is 31.2 watts. And pretty much if you have these pack of 12-volt batteries that you can put like a belt around yourself, you can make a portable unit. And the weight of the whole thing total would be 24 pounds with just one laser scanner. Again, this is something that's in progress. We don't have any results to show on. I'm going to skip the sensor placement stuff, but you can see that if you place sensors around the city, then you can visualize these things nicely and can catch the bad guys as needed. I'm also going to skip dynamic scene modeling. You can extend some of these techniques so that if there's an object moving with hands and arms and you have scanning equipment, then you can generate a three-dimensional model as a function of time, 30 times a second, for example. And this system we have actually built and we've published about it. There's a rotating mirror. There's a laser hitting it. And this causes a laser line on your object. And as the mirror rotates, this horizontal line goes up and down. And you project also with a halogen lamp and IR filter, you project vertical lines, and you can compute the depth along these lines and build the depth as a function of time. Pardon? It's a screen. It's a screen with a bunch of vertical strips on it. Pardon?
I've never seen the term roast before.
It's probably a foreign student using that term. But it's a screen with a bunch of strips going up to project the vertical. Actually, it's right here. You paste a bunch of stripes, and that's what projects the vertical lines onto the object. Okay? And then on here we have cameras that have IR filters and also a visible camera. The IR filter one will catch this signal coming from the IR halogen lamp. And the control PC and the sync generator and all the rest of it. That's the polygonal mirror with the horizontal laser. And so at the end, you end up having a sparse depth representation of the object as it's moving. You can interpolate that to get dense depth. And then you can, let's see if this video works. Probably not. No, it does. Random. So then you can reconstruct the 3D depth of this person as you go around the person to the right and to the left. And we only have one of these stations. If you duplicate multiple stations around it, you can get the back signal and merge those two things and get a true sense of the three-dimensional depth of it. So real quickly, other areas, streaming and also model update. These are areas that we haven't done any work in, but were quite interesting. We hope that in the coming year we'll be able to get to it. I'm going to stop right here, and this is the various places you can download papers and demos and models and various other things. And shall we end with, did we give all the demos, or is there more?
The big one.
Okay.
Show that really quick.
You mean the VRML model? Yeah. Okay, so I'm just going to stop and show you the, now it's a VRML model that has, it has airborne only.
You do a drive-through through this thing, or is that it doesn't give you good results when you do a drive-through at street level?
Fly-through or drive-through?
Drive-through.
Oh, it would look terrible. You do drive-through. We can do it just so you can see it, but no, it wouldn't look good because it's all airborne only.
The other thing I was thinking, why is the problem, maybe it's a stupid question, but why are you trying to remove trees from Mars? Because if you want to have a truly immersive experience, I think you really need trees, but otherwise it doesn't look like Berkeley.
street in Berkeley, right?
The problem is that at the ground level, when you scan the trees, you don't do a good job of making a model out of it. Because the resolution of the laser isn't very good. But you're quite correct. For residential, I'm personally believing more and more that we shouldn't be removing trees because it's so difficult to replace them with, I mean, the idea is let's remove the trees and then replace it with an artificial tree so that we can have a better model of the tree. That's kind of the thinking. But that process, as time goes on, I'm beginning to believe is more and more difficult and not such a good idea.
And probably less immersive as well.
That's true. That's true. I think that's just about, yeah, question.
Yeah, I have a question regarding the way you're fitting a geometric model to your facade.
Right.
I guess you do a foreground removal.
Right.
And then whatever points you're left with, you do a triangulation.
Right.
But isn't that prone to basically aliasing in progress? You're going to have a lot of regions with the undersampled, let's say parts of the staircase or small pillars, and you're going to have very few samples on those features. And
because we remove things.
Yeah, and so you're not going to get a very good geometry for those features. And that would add unnecessary clutter to the model, in my opinion. Does it make sense to do some kind of low-pass filtering on these points before you actually fit a model? And one way to do that would be by some kind of model fitting, maybe a procedural model fitting. Is that something you consider?
Yeah, it's possible to there are people who do procedural model fitting. For example, Ulrich Neumann at USC does something along those lines. However, his methods are semi-interactive. So there's a user that comes in and clicks on things and says, you know, fit a parabolic surface here and fit a plane here, fit another plane here, etc. But I think your point is quite well taken. And philosophically, that you're also bringing up a very good point. Why remove things and then make up data? Why not try to fix what you have and do the best of what you got without extracting, kind of, because the model at the end also looks a little bit less photorealistic.
I guess I'm also saying removing some features from the geometry which you're sure you won't be able to do a good job of spacing.
They said that there's another talk that needs to, let's discuss this offline. Thank you.